So example 2, a bacterial population starts with 4 million bacteria and triples every 30 minutes. Use our equation to solve. So what we're going to do is solve our K value. So let's go ahead and do that. So part A. So if we have 4 million and we triple, that means we're going to have 12 million, right? So that's our new AT. This is actually our A sub 0, right? Because that's our starting amount. Then we triple, so that's our A sub T, or A parentheses T. And we have 30 minutes, which is our given time. So we're going to start with 4 million. We have E still. Then we have our time, which is 30 minutes. So let's go ahead and make that out of hours, right? So in order to do that, so let's make it out of hours. We have 30 minutes. How do we do that? We go 60 minutes times 1 hour. We're going to get into dimensional analysis a little bit later in this module. So let's go 30 minutes divided by 60, which is just 0.5, right? We also know 30 minutes is half an hour. So 1/2 is 0.5. So let's go 0.5, and we don't know what the K value is, right? That's what we're solving for, but this is our time. So now we can go ahead and divide by 4 million on both sides. So really we're left with 3 on the left-hand side. So what we're going to do, so we have 3 is equal to e to the 0.5k. So this became a lot more simple. So now we can go ahead, take the natural log on both sides. So when we do that, right, when we take the natural log of e to the 5k, that becomes 5k times the natural log of e. So let's go ahead and write 5k times the natural log of e. This becomes 1. Then we just need to go ahead and divide by 5 on both sides. So we're left with k is equal to the natural log of 3 divided by just 5. So let's get our calculators out. So we have 3, take the natural log of, and then we're going to go divide it by 5, and we get 0.2197. We're just going to take it to 4 digits. So 0.2197. So this is part A. Let's go ahead and solve for part B. So let's find the general equation to represent this bacterial exponential growth. Well, that just means we're going to have A sub t. Then we still are always going to have 4 million here, raised to the e. And then we have this 0.2197 t. So that would be our general equation, and that's it. So we just want to make sure we have the same starting amount for always, but the things that will always change is our t and then our ending amount, or whatever amount given at that time. So that's our general equation. So all we have to do is plug in our starting amount and our k. So now our next step is part C. So we're actually just going to use how much bacteria is left at 45 minutes. So what are we doing? We're solving for this in part C. So we have 45 minutes. Well, 45 minutes of an hour, that's going to be 0.75, right? So or you can go 45 minutes divided by 60, which would give you 0.75. So we still have the same starting amount. E raised to this 0.2197 times let's do x to show 0.75 because of this decimal. So now let's go get our calculators out. So remember, my calculator wants me to go 0.2197 times 0.75, which gives us another decimal. We're going to take the inverse, so we get to e. So we're going to, whatever this came out to be, we're going to take e raised to that power, and that is our 1.1791, and it continues on. Then what we're going to do is go ahead and multiply this by 4 million. Let's make sure that I have enough zeros, which I do, and then we can go ahead and press enter, and we get our solution. So we got and what is this? What are we looking at? Well, we're looking at bacteria. So we're going to round to just the nearest whole number. So we get 4,716,511 bacteria. So that would be our part C.